say it ain't so. That's what you wanted, right? That's what you're looking forward to. The title on this thing's doo-doo. But yeah, double integrals over polar regions. Okay, let's look at this beauty right here. Like, if I tried to integrate just a circle, right? Like, do I go dy vertically? Do I go dx horizontally? Not really. Like, in this case, I could do either, but let's say I go dy. So x is going to be from -1 to +1, and y is going to be from here to here. Do you want to plug in these? You want to plug in these bounds and do these trig sub? I'm just asking. I'm just asking. But what about here? Oh, between this circle and this circle. Wah 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 wah. You don't want to do that. You don't want to do that. I don't want you to have to do that. So, how about this? Let's just call this r equals 1. And let's just call this bound r equals 2. And let's realize that if my theta goes from 0 to 2 pi, it'll do a full lap around this circle. If my r goes from 1 to 2, I'll be only integrating this part with my radius would be between lengths 1 and 2. And I will have covered, if you think of all the places that r is between 1 and 2, and all of the thetas between 0 and 2 pi, I would be slowly painting in this whole terrifying nightmare eyeball. But we have one huge change that we have to make. Already theta. So not only do we have x equals r cosine theta, y equals r sine theta, we got x squared plus y squared equals r squared, everybody's favorite Pythagorean theorem. We have already theta. You need to use already theta anytime you're changing from rectangular to polar. I'll do a little bit to show you why. Whereas before, we were trying to find all these little rectangles and then kind of like sweep them across the region, where we'd have to find the area of this thing first and then sweep that dA area around the region, where the dA would constantly be changing, and this would be giving me my height times area would give me volume. Well, here, the area of this is not so easy. It's not just, you know, delta x times delta y, or dx times dy to get dA. Here, we're a little bit more complicated, where I'm trying to fill in, this is the big zoomed out version of this thing that we were just looking at. Here's the zoomed in, just focused on this one highlighted square, where I realized that, hey, this would be my d theta, my change in theta that covers this infinitesimal. This would be my dr, my differential of r, that would cover that infinitesimal. And so this length here could be measured as r times d theta, and therefore this area is what it becomes, is approximately r times dr times d theta, already theta. So as long as you sound like a pirate when you're integrating polar regions, you're in good company. Again, another video where I'll be pausing a good amount, just because, man, there's just a lot of tedious little work, and I believe in you. I believe in your integral abilities. If I didn't say that enough, I believe in you, and I believe in your integral abilities. So let's get integrating. So not only do I need to change my differential, I need to change my function. And to be honest, this change, we will show you in greater detail later how this change is measured and how we know for sure it's already theta. Today you're just kind of taking, like, this is like a little bit of a fake proof, and this is, you're just going to have to take my word for it. So I have to change my function to be in terms of r and theta, my differential to be in terms of r and theta, and my bounds to be in terms of r and theta. Again, this is the upper half plane bound by these two circles, kind of like that first one we saw, except it's just the upper half. So it's just this from r equals 1 to r equals 2. Well, I can already kind of see where these things are coming from. Just taking a moment to talk about the bounds. My thetas are going to start here at 0 degrees. Not degrees, g's, 0 radians. And move its way all the way over here where I have pi radians. My radius, it's not going to go from 0 to 2 because that would paint this whole region. No, we're just looking for when my radius is at a minimum of 1 and a maximum of 2. And it'll keep drawing those bands from 1 to 2, 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 as theta cycles around from 0 to pi. That's the visualization of what these bounds are. Now to change this inner function, I just use those reminders that I gave you up here. X equals r cos theta, y equals r sine theta, and we're off. So this becomes 3 r cos theta, brain fart right there. This is going to become 4 r squared sine theta. Now I take this whole thing and I multiply by hardy theta, even though I already switched out my r's and thetas. So I should probably distribute just a little bit here to help me simplify before I go ahead. Again, these will start to look really familiar as you continue to practice them. This is definitely a practice makes perfect lesson. Okay, now it's time to start pausing. Again, we know how to do iterated integrals. This can become a cube. This can become a fourth power. I'm going to plug in the bounds. You're going to see that. And then I'm going to probably continue on from there because I see this incoming. I forgot to write it. If it's y squared, it's sine squared. It's sine squared. And this problem just got more fun if you didn't catch it. 8 cosines minus 1 cosine is 7 cosines. That's 16 sine squareds minus 1 sine squareds is 15 sine squared theta. Now this is probably going to be where I'm going to split it because this is an easy integral. This is a toughie. So if I took this one over here, this one should probably turn out pretty quick. 7 cos theta d theta would become 7 sine theta from 0 to pi, which is just 0 and 0 is just 0. Lame. But the other side, not lame and not easy. I'm going to use that all-powerful, all-wonderful substitution. 1/2 1 plus. Oh, I'm getting ahead of myself. What am I doing? 15 1 minus cosine squared theta. And remember, cosine squared. My cosine squared identity that you're going to use a million times in this lesson is 1/2 1. Oh, now I got myself second guessing. Hold on. 1/2 1 plus cosine 2 theta. I almost wrote minus. And so this is going to get subbed in here as well. So I'm going to have 15 times 1 minus 1/2 is 1/2 minus 1/2 cos 2 theta. That is definitely integratable. And so I'll throw this thing in from 0 to pi. 15 over 2 minus 15 over 2 cosine 2 theta d theta. From 0 to pi, I get 15. Oh, no, I'm done. 15 over 2 theta. 15 over 4 sine 2 theta evaluated from 0 to pi. Here I'd get 15 pi over 2. Here I'd get 0. Here I'd get 0. There I'd get 0. 15 pi over 2. What a good day. 15 pi over 2. What a good day. On to the next one, folks. The volume of the solid bound by this plane and this paraboloid. It is important to be able to picture this paraboloid in your mind. So let's throw it up in the Desmos 3D for you real quick. Z equals 1 minus x squared minus y squared. There she is. So we're just finding the positive part, like this volume. The volume of this green dome above the blue sheet. And so I kind of can tell that I have a couple things happening here. Right, when I flatten it out like this, I see that my radius is a radius of 1. But then at the top, if I think of the tippy top, what is my radius? Well, it doesn't extend out at all. So my radius in this case is going to go from 0 at the very top, and it's going to grow and grow and grow and grow and grow and grow until it reaches 1 at the bottom. And my theta is going to go 0 to 2 pi. So now let's set up those bounds and let's go, y'all. Again, this function needs to turn into a function of RDR, or R's and thetas, to eager to be a pirate. So this becomes z equals 1 minus r squared. In case you're wondering where those r bounds came from, you could plug in the lowest point and the highest point. That is worth talking about, as I'm getting a little bit too excited here as we're trying to become a pirate. The highest point on this thing is when z equals 1. And when z equals 1, 1 equals 1 minus x squared minus y squared, which we just learned is 1 equals 1 minus r squared, and so that would be r is 0. And then all the way at the bottom, 0 equals 1 minus r squared would give me r is 1. Just showing you some context if you don't have the Desmos 3D out to see what my bounds will be. So now I'm just going to be distributing, and this one actually goes really quick now that the integral is not. Don't forget your bounds because you're having so much fun like me. I still have to evaluate from 0 to 1 before handling the d theta. I got 1/2 minus 1/4 and 0 and 0. Now from 0 to 2 pi, I'm integrating 1/4 d theta. Well, that just becomes 1/4 theta from 0 to 2 pi. And that just becomes 2 pi over 4, that's pi over 2. Minus 0. Right, like all of a sudden it starts to really roll down here. When you get to here and you see no weird sines and cosines, all your r's and thetas are kind of separated. It's just like boom, 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 boom. Straight to my answers. The easiest place to make a mistake, though, the question of the day is, when are area and volume equal? Oh, well, thank you for asking, students. If area is length times width and volume is a length times width times height, the only way these two things could be equal is if height equals 1. Well, when we're in Calc 3, we call height z. And z is a function of x and y. So, if I want to find the area, I just do the double integral of 1. Because the area will be equal to the volume when the height is 1, and the length and width are my bounds, and the height is my z, my integrand. So use double integrals to find the the 4-leafed rows. That's cosine centric, so it likes the poles. I'm so ready to get this wrong. Oh my gosh, striking fear into my own heart. I'm going to pause for a second, make sure I don't blow this. You know when I got scared? I forgot that it's 2 times theta. So as I was coming in here, I was like, how is it going to extend along this axis to make a pedal up here? Because when I multiply pi over 2 by the 2, it becomes a full pi, and cosine is happy once again. Again, I'm not graphing this in order. I'm just graphing this shape for the sake of showing it. Ta-da! If I'm graphing one leaf, if I'm grabbing one leaf, it's going from about here to about there. Hopefully I recognize those angles as pi over 4 and negative pi over 4. Also, I can see that it's going to go to 0 there, because when I do 2 theta, it would get to 0 for cosine at these values. Also, it's worth noting, hey, what is this maximum coordinate here? And that's going to be 1, 0. So I see my radius maxes out at 1, but I don't think that's exactly where I want to go. Because my radius, as it traces, it's like doing this. My radius length, it's bound by the curve. And the lowest place it is, would be 0. And the farthest my radius is, I know that makes you very excited to let a function be your bound, but it's going to be good. Why wouldn't it be good? You got to trust me sometimes that I love calculus and I love you too. So my integrand is 1. Hardy, hardy theta. Can't miss it, folks. You can't miss it. That's why I'm saying it so obnoxiously. Part of me wants it to be the first thing you say to me when you see me in February. Hardy, hardy theta. Again, just continuing on with my wonderful integrating self. This is where I feel like I'm going to make a mistake, but you got to believe in yourself. You got to trust yourself. Go slow and steady to win the race. Here. Oh, no. Oh, no. Mr. P. So, again, this is a cosine squared. So, even though this theta looks ugly, sine squared of 2 theta plus cosine squared of 2 theta still equals 1. Because sine squared of anything plus cosine squared of anything is still 1. Like my substitutions, my double angles still works. Cosine of some angle is still, or cosine squared of some angle is still 1/2 1 plus cosine double that angle. So in this case, when I have cosine squared 2 theta, it's going to become 1/2 plus 1/2 cosine 4 theta. Again, it's not nice, but it'll integrate. Like if I, instead of will it blend, we could be chanting, will it integrate? And in this class, the answer is always yes. Okay, be careful. I had a 1/2 out here that I didn't account for on this. So this is actually going to be 1/4 plus 1/4 cosine 4 theta d theta. Now I can antiderivative 1/4 theta plus 1/16 sine 4 theta. Evaluating theta from negative pi over 4 to pi over 4. Well, would you look at that? The sign's going to cancel. Like, this keeps happening. And I honestly don't know if I have a good explanation of why. But it just seems to happen as you practice and as you go through. These trig functions drop out and disappear. Maybe it's some kind of sine squared, cosine squared thing. But anytime I do this substitution, very, very, very often, it drops off the face of the earth and we just have a nice answer. This is going to be what? Pi over 16 plus 0 minus negative pi over 16. How nice. And another 0. So I'm just not going to write it. And so I end up with pi over 8 for a final answer. Again, like I'm blowing through these because it is just like you got to know that z equals r squared. Like that should be instant. You see x squared plus y squared, you think that's r squared. Now I head over here and I make all my substitutions. On the right side, on the left side, I have r squared. On the left side, I have 2r cos. Maybe you're slowing down now. Maybe you're like, what is that? What does that look like? I hate doing math backwards. Okay, maybe you're not quite seeing it yet. Maybe you're not quite seeing it yet. What if I did this? Don't write 0. It's a circle of radius 1 that's shifted to the right one. That's ugly. But, again, the smallest my radius is at 0. Right down there. But then every other moment for my radius, it's trapped inside this r equals 2 cos theta that we found up here. And guess what? My angles, well, it's a bit hard to see because you want to do the pi over 4 chop, but you know it's a full circle, and so you know that there's this point 0, 0. You know that it comes in all the way really close, so it actually goes from negative pi over 2 to positive pi over 2. Basically everything in this half over here. Now that I have my bounds, I go. We ride. And my integrand. Hardy, hardy theta. Can you believe how much fun this one is going to be? Now I'm definitely going to be pausing the video as we work through this one, because it's not going to be nice. This becomes an r cubed. It's going to be 1/4 r to the 4th. no, 2 to the 4th power 16 over 4, that's 4 cosine to the 4th d theta. Hopefully you recognize that we're about to have a great bit of fun. I'm going to take you on the side quest, and then I'm going to pause through all the calculus. Cosine to the 4th. Oh, that's cosine squared times cosine squared. Well, I know that cosine squared is 1/2 plus 1/2 cosine 2 theta. And this would be 1/2 plus 1/2 cosine 2 theta. And if I FOILed these and multiplied them, I'd have 1/4 plus 1/2 cos 2 theta plus 1/4 cosine squared 2 theta. Well, guess what? Your cosine squared 2 theta is this guy over here. So we're going to make that substitution down here as well. And it was 1/4 of this thing. So it's going to get a little bit yuckier. Right, like, I believe in us to do this. That's 1/8 and 1/4, that's 3/8. That's still a 1/2 cosine 2 theta. And this is going to be a 1/8 cosine 4 theta. And that is a very integratable function. I'm going to have to multiply it by 4 when I plug it back in. But we can do it. Yes, we can. Spot check, spot check. Did you plug it back in correctly? I definitely made a mistake. No. I feel pretty good about me. Still feeling pretty good here. 0, 0. 0, 0. And that's how you do calculus. Come on, man. If that don't get you fired up when you get that question right, maybe different things get us going. Because, like, that, when it comes out 3 pi over 2, I mean, when it comes out 3 pi over, it's extra awkward that my video froze for a moment. I love calculus.